start stream button. Let's see if this did what we wanted to do. We are trying something new here. Because for those that might be watching, and have watched previous pwn.college things and are aware of how semesters work, we are not in a semester. Oh boy. Okay, I think that sounds right. There we go. Yeah. All right, cool. Works on the phone. Okay, so we started the stream. The semester is over. Why am I live streaming? So the reason I'm live streaming is I'm trying something new here. And the thing that I'm going to try here is to learn about something that I've never done before. So one of the things that I've noticed is while teaching 365, 466, all of this pwn.college material, pwn.college, awesome. We never get to do like the how do you learn something new perspective thing. So what I'm going to try and do is I'm going to try and live stream this. We'll see how it goes. We'll see. I don't know. This could be a one and done situation. I might do it multiple times. Who's really to say? And what I'm going to try and do is learn about something that I haven't done before. And we're going to do a few things as part of that. I'm going to build a new dojo module. This is the idea. We'll see. This might evolve very rapidly. But here's what I've got in my head. We're going to create a new dojo. And in that dojo, we're going to create a new module. And in that module, I'm going to learn about something. I think I already know what the topic is. We're letting the cliffhanger go for a moment here. Largely, I'm kind of interested in seeing how good ChatGPT is at teaching me about that topic. So that's like another little side goal, is to like see what is the education experience right now on ChatGPT. Can I learn about a topic that I maybe have a slight surface understanding of, but like, can we get deep into an understanding with the assistance of ChatGPT? Obviously, if we need to go to the internet and just start Googling things, that is going to be totally fine as well. I'm not like doing some crazy thing. Oh, look, there are people in the chat. Wow, look at that. I was wondering if people got notifications or something. So this is the idea of what this live stream is going to be about. I have no idea. I might do this on a weekly basis, or maybe I'll do it twice a week. I don't really know. We don't really have high expectations for this. My current thought in my head, though, is that I'm going to go for 2 hours today. 2 hours seems like a good amount. I don't know if I'm really enjoying it. Maybe I'll go for longer. Unfortunately, I got real work to do. But I wanted to try this out. Let's learn about a new topic and build a dojo along the way. Probably we're going to do a little more learning before we do dojo building. We'll see how much we kind of do both simultaneously. And the hope is that maybe we have like an artifact here that is an educational resource for others, either through these videos, these live streams, or in the form of, an actual module and people type code. We always love people typing code, but some people like to watch videos, whatever. I don't really care. We'll see where this goes. The hope is to kind of build some hype around the idea of community dojos to some extent, in which other people have created. So in this case, this is Robert's dojo. He teaches people about ARM, which is pretty cool. I know that Jan created one about Linux that's a work in progress. Jan also created one about Bash, which is pretty cool. What else do we have? I don't know. Other people have, this is like Kyle has one that just has a couple of challenges, which is still cool to see. I know this dojo I've seen people talk about, which is pretty awesome. Right? We've got all these like community dojo things, like Hydra dojo. We got all this stuff. And so I'm going to try and create one as well, while showcasing the entire process of a new topic that I know very little about and going from there. So the topic, let's get into it. What is the topic? The topic is going to be bootloader. So when I teach 365 and think about computers from the perspective of the kernel. So one of my core abstractions is that we have this thing called the kernel, and for all intents and purposes, the kernel is the interface to the computer. The kernel provides all these facilities. Everything you do is you do like a syscall, and a syscall gives you capabilities, whether it's for a process or a file or all of these kernel level things. Now, of course, that is not true, right? The kernel is not at the bottom of the abstraction layer. Obviously, you go all the way to transistors. I'm not going to transistors. Maybe one day we'll go to transistors. But what I'm going to do is I'm going to try and peel back one more layer. Okay, we're going to get rid of the kernel. The kernel no longer exists. And all that exists is this hardware that can run x86 64. And my brief understanding, so, you know, I just graduated my PhD, so you'd hope I have some understanding of computer science here. I have a brief familiarity of terms like bootloader and like BIOS and stuff like that. And I want to start writing code that just goes straight to the hardware. And my understanding is probably the way that we're going to do that is we're going to do a bootloader. That just is kind of basically the entry point of code. I think technically the BIOS does its thing first, somehow initializes something. I think that's like even closer to the hardware. I don't know. I don't think we're doing a BIOS. I think we're doing a bootloader. And it's basically the entry point to the computer. There's no kernel. There's just bootloader, x86 instruction runs, x86 instruction runs, x86 instruction runs. No Linux kernel. We've got like, I don't know, I think real memory, you know, not virtual memory, or what's it called? We got physical addresses and stuff. I don't know. We're going to find out. Okay, I have a surface level understanding, but the goal is to develop a stronger understanding. And the tool we're going to use here as part of this that I do have some experience with is QEMU. So QEMU is going to be our virtual hardware, or, you know, more commonly referred to as virtual machine. And I am going to use QEMU and a Hello World bootloader. This is the first step, all right? So we got this thing called QEMU system x86-64. Well, I guess that actually does do something immediately. VNC server running on this. I think this VNC server is our virtual display. So basically, QEMU has, by default, I don't even know really. By default, it has like an x86 single core chip running. I don't know what the default amount of memory is on our system. We can figure that out as soon as it matters. It's got like a VGA monitor basically plugged into it. It's kind of how you could think about it, I think. Which has, I guess you view this VGA monitor through a VNC server. So I know I've done this sort of thing before using QEMU. Let's actually see. New terminal in editor area. I think I've used, okay, so I do know about VNC and I do know about QEMU. There's like something we have installed that allows you to see, for example, the desktop. So on pwn.college, on pwn.college, we have this idea of the desktop, right? Which this thing is going over VNC, and in particular, it's going over like no VNC, which puts it in the web browser. I think we can get a similar thing going. So let's get that similar thing going first. Before we even have a bootloader, let's see what the heck is currently on our screen. So I know VNC WebSockify, this is the thing. So you'll see I did prep just this part. I've investigated this. This is going to, I think, an IPv6 IP port 5900. This thing right here, I think, I run this command. I think this means now in our browser on port 80, I can view this thing. So let's go back here. If I go Firefox localhost 80, I think we're going to see, we go to vncauto.html. Okay, look at this thing, right? So you'll see this is what our screen is. We got some text on our screen. This is the QEMU is doing this. I know QEMU has a BIOS. The BIOS probably tried to parse a disk or something, and it says boot failed, could not read the boot disk. It's probably trying a whole bunch of ways to boot from a disk. I really am not sure. open source network boot. It looks like there's some sort of network boot firmware where my understanding is it's possible to boot from the network. I have no idea what IP address it's trying to hit to do that by default or whatever. And it just says no bootable device. And I don't know. I don't know if there's a keyboard. I think there's a keyboard, but probably doesn't respond to the keyboard at all, right? All we got is hardware here. Or close enough to all we have is hardware. So that's cool. I don't want to do this though inside of the pwn.college desktop. I know I can route this through because I've done it before. It's challenge question mark path equals workspace challenge. What is this called? I think like Websockify. I think if I go to this path, I'll also get that booted. Yeah. No. Inspect. Where did this go? I just don't want to go through the pwn.college desktop. It goes to /Websockify by default. Path workspace challenge Websockify. I know I've done this before. Challenge. PNC auto this. There we go. Okay, now we can get rid of pwn.college desktop. We don't need like Firefox in our virtual desktop thing. Okay, this just routes all the way through. So now we can see our monitor. Okay. Can you make the text be bigger? In general, text is hard to read on stream unless pretty big. Yes. Especially since our monitor is pretty small. Like I think you need software if you want resizable monitor. I'm guessing this is like 800 by 600 VGA monitor by default. So that's nice and zoomed in. None of this text should matter. How is this text? Is this text like big enough? Or do we want even bigger? 1, 2, 3. We'll do +3. Hopefully that's good. This is fine. Okay, and we'll make sure ChatGPT 1, 2, 3. Hopefully that'll be big enough when I start using ChatGPT, which is imminent. Okay, we got our setup done. So we've got a monitor, we've got our virtual machine, right? This literally just booted a virtual machine. We didn't even specify a hard drive. We're gonna have to specify our hard drive if we have any hope of getting some code into this machine. Let's do that. So we've got kind of step -1 taken care of. Okay, so let's go ahead and kill our virtual machine, which we can see kills that. And let's talk to ChatGPT and tell it I want to write an x86 64 bootloader with QEMU that prints hello world to the screen, right? This is going to be our first test case. Creating, running it involves several steps, writing the bootloader code. Okay, bootloader will operate in real mode, 16-bit default mode when an x86 computer boots up. Below is a minimal example using assembly, NASM syntax. What the heck is this? Okay, so this is a new instruction that I've never seen before. Offset in video memory. Wait, did I say BIOS or bootloader? Okay, origin BIOS loads the bootloader here. Okay. It's gonna assemble this thing with NASM. I think this thing is going to make sure that the file is like, this is going to make it be 510 bytes, and then this will be another 2 bytes. So I think this thing needs to be 512 bytes in size. Like the computer just, the BIOS, I don't even know what, if it's where it's baked into, but some mechanism low in the hardware slash software slash that blurry boundary looks for this 512 byte thing. And I think it's like literally looking for this identifier at the end of that, like the last 2 bytes of the 512 bytes has like AA55, and it's like, all right, that's my thing, go to the beginning of this and start executing. So the very first instruction I think that's going to execute is CLI. This is stuff for NASM, I think. It's going to say like bits 16, as in we're in 16-bit real mode, I guess, whatever the heck that actually means. Org 7C00. Origin BIOS. I'm guessing this is like an addressing, like this actually takes place at address 0x700 or 7C00, maybe. All right, we're gonna start by copying this code. You can see it's doing a whole bunch of stuff. I have no idea what the CLI instruction does. We got a lot of stuff we're gonna be figuring out here. We are gonna do make dir boot cd boot code server. What does ChatGPT want me to call this thing? Bootloader.asm. Bootloader.asm it is. Okay. I'm gonna zoom out a little bit. Yell if this size is also too small. Hopefully someone will say if this text is too small. I will keep periodically looking at the phone to see if people have comments or thoughts. Okay, so again, I really have no idea what this instruction does. I'm hoping ChatGPT can just one-shot this. It looks good. Okay. Yeah, hopefully this size will be nice. I recognize obviously like that this is, actually I don't recognize this. What the heck is this? This does not look like ASCII H. White on blue attribute. What? Okay, wait, 1E is consistent. 4.8, that looks like an H. 6.5 is an E. I have no idea this 1E. I guess it's white on blue. Okay, let's just see that it does what ChatGPT thinks it's going to do before we do a deep dive on this. Okay, so we need to assemble this thing. So nasm-f bin. I think this is just going to produce 512 bytes into bootloader.bin. And we're going to start up QEMU with a drive. It's a raw drive. I don't know what other drives there could be. File equals bootloader.bin, and those 512 bytes are just going to get inserted into the hardware, and the hardware slash that blurry boundary, I don't know, firmware, BIOS, I have no idea what the heck the right word is, takes care of the rest. Okay, so let's check that out. Obviously, you could go arbitrarily deep with this. This is the layer I am shooting for. You go all the way to the transistor. I'm used to the kernel. We're going to the bootloader though this time. No kernel. We're done with kernel. Bootloader.bin. Okay, is this thing actually 512 bytes like I think it is? This thing is in fact 512 bytes. Can I like obj dump this thing? Nope. Does file recognize what this is? It is a DOS MBR boot sector. Okay. Then let's do this QEMU. QEMU system x86 64 drive format raw. Okay, running there. Okay, we should see this in the browser now if we refresh. Look at that. And we just typed right over the start of whatever the heck this thing is. Again, right, my keyboard doesn't do anything. We're pretty sure we have to start writing code if we want the keyboard to do something. I do think that by default, like the keyboard is plugged in, like as a hardware concept. but we're gonna have to write code to do something about that. But we got hello world with blue and yellow because ChatGPT wanted blue and yellow. Cool. So let's go ahead and, because I think what we're going to be doing a lot is running this command and also our NASM command. Let's create like a little, like, we'll call it run.sh, but it'll also do building. Could be a make file. I don't know. I like this. Keep it nice and simple. And we'll also NASM this thing. And because I'm thinking about it right now and I don't want to hit this bug later, I'm pretty sure if I do bin sh-e, I think -e will make it so, oops, man, sh. I think -e will make it so if anything bad happens, this man page is terrible. I just want to search -e. I think this makes it, nope, not that -e. Let's see. I think it makes it so that if one of these commands fails, it just stops executing, whereas the default is not that. Let's see. Also, also let me know if the stream is ever lagging or something like that. I don't know what kind of insanity we might run into, so it's on you guys, because it's going to YouTube after. So the YouTube people, if you're sad, blame the Twitch people for not yelling at me about quality. Okay, let's make sure that run.sh, the heck? Where's my run.sh? Plus x run.sh. Okay. I think x will make it print every statement. Yeah, so false ran and we failed out. Okay, on the other hand, this does that. Cool. Now we also have this guy running in a different terminal, which we'll document for ourselves. I don't want to deal with like starting this thing if it's not started. You need logic for that. I don't know. I don't want to deal with it. Let's document this though, just right in our run.sh. That command is something, and let's also document this URL. Okay. And then let's run.sh. Let's refresh. We got hello world. Cool, cool, cool. I wonder, the next fancy thing to do will be as soon as bootloader.asm changes to restart this script. I think there's a way to do that with like iNotify. Probably don't need to get too fancy yet, but as soon as I'm getting annoyed with restarting it, we'll look at that. And I said that people should yell at me if there's a problem. I don't see a problem. Okay, cool. Okay, so what happens if I get rid of this 1e? I just do like 0, 0. Does that get rid of blue? Nope. Does get rid of H though. What about 1F? Could just not guess at this, but you know what? Sometimes I like a little bit of guessing to see. Oh, look at that. Okay, 1F is not yellow on blue, it's white on blue. So what about 1? So that's F. What about CF? Is that gonna be a different background color or something? Sure is. CF is, so that first byte is the color of the background. This byte is the color of the text. Cool to know. And then of course this is ASCII. Now, okay, first question. We got a few questions actually. Okay, so this is saying we have text mode video memory at address B800. So my understanding of how the computer really works, right? Again, another layer of abstraction I'm sure is sitting somewhere in there. So in 365, in Intro to Cybersecurity, I always talk about how the way you interact with the world is through the syscall instruction, which is true when you've got this kernel thing that's like abstracting everything away or whatever. I think in reality, though, again, who knows at what layer of abstraction, blah, 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 blah. In reality, you just have these magic memory addresses. Like something about the hardware just knows that at B800 is the address of text mode video memory. And this thing is, I don't know, 100 bytes, hex 100 bytes in size, or hex 800 bytes in size. I don't know how much text mode video memory we have. We could probably ask Jippity if we wanted to know. But this is that. Okay. I don't know. Okay, I've heard of interrupts before, right? Like I think, for example, a syscall is an interrupt of some sort. I don't know what the heck this thing actually is, so I don't recognize this. Of course, you know, I'm just gonna got to pick at some depth what we're gonna talk about here. Hopefully you've seen x86. I'm kind of assuming you have, right? We're moving this into a 16-bit register named AX, then that's going into ES, then this XOR is zeroing out DI, which is probably also a 16-bit version of RDI, if I had to guess. Then we put this into AX. Don't know what the heck this instruction is, but it seems to be doing, I don't know, STO sounds like a store or something, like store something word maybe. Jump $, this is a while true loop, just keep jumping to yourself. This fills it out. This is our boot signature at the end of our bootloader. Okay, so this instruction and this instruction, I have no idea. So first thing I'm gonna do, I'm just gonna get rid of it. Okay, we're no longer clearing interrupts, whatever that means. What is our computer going to be sad about that? Do we need to clear interrupts? Who says we got to clear interrupts? We don't need to clear interrupts. Look at that. We still boot just fine. We'll see why ChatGPT thinks we need to clear interrupts. And I'm guessing just based on the structure that this goes into AX, this goes into ES. This is probably like incrementing ES every time. It probably does like a inc ES and writes to this address in memory. Like it's probably like put this value into this pointer and add 1 to it, and then it just keeps doing that. Maybe, I don't know. Let's find out. What the heck? Oh, I guess it didn't need to do this twice. Okay, let's see. ChatGPT, tell me what the heck is going on. What's the deal with the CLI instruction? Why do I need or not need it? What's the deal with STOSW? What does that thing do? Clear interrupt flag in assembly, especially disables interrupts by clearing the IF flag. When interrupts are disabled, the CPU will not respond to interrupt requests from hardware devices. Okay, so my understanding of interrupts is that at any point something can generate an interrupt. For example, I think there's like a timer interrupt where like every 100 milliseconds this interrupt occurs, which changes the address that you're executing at, basically. So that, for example, in a modern kernel, you might want context switching of your processes to occur every 100 milliseconds or whatever basis it occurs at. And you want the hardware to just like provide this interrupting functionality of doing a process switch every 100 milliseconds. Interrupt comes in, which really just suddenly aggressively changes the instruction pointer somewhere, and then code's executing there to take care of that and do a context switch. So this, I guess, just makes it so no more interrupts. You don't get interrupts anymore. Okay. So I guess this is a safety thing. That's why we could get rid of it. Probably no interrupts are being generated. So this is probably, again, it's a safety thing. What if an interrupt did occur? We want to not deal with that. We want to don't interrupt me, basically. And I guess this is saying avoiding potential complications from an interrupt service routine, ISR. So if you haven't set up an ISR table yet, so what address do we go to when there's an interrupt? Well, that's up to the interrupt service routine table, I guess. Simplifies, don't need to handle asynchronous events. Okay, we should probably, until we have an ISR table thing that we care about, no interrupts. Okay, default state upon boot. Default. The CPU starts with interrupts disabled until the BIOS enables them. You start executing the bootloader immediately after the BIOS hands over control. You haven't re-enabled interrupts. They will still be disabled, making the CLI redundant at this stage. Okay, so probably we can rely on the BIOS to have kept that disabled. So this is just a redundancy thing. So we really don't care about that, but it's good to know about. Stow SW instruction is used to store a word 16 bits from the accumulator register AX into the memory location pointed to by the extra segment ES and destination register DI registers. Okay, so exactly what we thought. Stores the contents of AX at the address. So we're just writing to memory. STOSW just writes to memory. Can I just use a move instruction instead of stow SW? Probably this is just a shorter instruction. Let's see here. Yeah, see, I could do this if I wanted to. ESDI, 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 ESDI. Oh, and then also do our own add DI too, right? So it's the same as this, I think. If we want to do that. What is the ES register? I see that someone has asked. Well, what is the ES register? I've heard of it. It is a segment register. Why do I need to use ES register? Tell me more about segments. Do they really matter? Okay, especially in real mode, CPU memory management relies heavily on segments. So this is just like another memory concept that exists that we don't have to use really when we're writing our x86 64, when we're dealing with like Linux and blah, 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 blah. This is like segments, my understanding, are a lower level concept / I think when you used to do like 32-bit programming, they were more relevant. But now that we have like this full massive 64-bit address space, you don't really care about these segments. I think they're basically like a concatenation to the address, as in like 0x4200, like this is a 16-bit address, right? And if we only have 16-bit registers, blah, 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 but we want to address more than 16 bits of memory, like if we really want to address, like, let's say 114200, I think you put this 11 into the segment register, and then it knows to look at the 11 part of memory, and it basically just concatenates it, right? So that it does the full address. I think this is how you get around like a 16-bit limitation while addressing actually more than 16 bits of memory. Let's see if Jippity agrees with that. Memory segmentation. This method used by x86 processors in real mode to extend the addressable memory space beyond what can be directly addressed by the 16-bit registers. Here's a breakdown, 16-bit limitation, right? So this is, you can only do 64K of memory. However, the processor can access up to 1 megabyte of physical memory. So this segment thing is how you get that concatenation to go further, even though you only have 16 bits to play around with. Because when we boot it up, the thing to remember is we're in 16-bit real mode. The CPU doesn't even start, like I'm pretty sure if I do move RAX42, I don't know who's going to yell at me. Probably the assembler is going to yell at me. Yeah, look at this. Error instruction not supported in 16-bit mode. Like, you don't get to move 42 into RAX. There's no RAX right now. We're in 16-bit mode. At some point, I think we can switch the processor into 64-bit mode. I don't know how soon we get to do that. But we start in 16-bit mode. I have no idea why. Probably it's some sort of legacy compatibility thing, but really not sure. To access more, yeah, so you get these 4 segment registers. So in general, right, you might have your code in one segment, some data in another segment, a stack in another segment, I guess extra in yet another one. So, So ES, I guess, is our extra segment. Presumably all of this code right now is being addressed relative to CS, right? If I had to guess. And this is how we're selecting, like we're basically making this segment occur, right? As in, like, this is the segment I want to refer to. And I guess stow SW just inherently goes relative to the ES segment, and uses DI as the other part to offset. And then stow SW just knows it's interacting with these things, and Intel created this small little instruction because it's such a common operation early on, and you have 512 bytes to fill in your instructions. You kind of want small instructions to be able to fit into your bootloader. That's probably what's going on here. Okay. So yeah, physical address is calculated using segment and offset values. The actual address is computed as segment times 16 plus offset. This allows the CPU to reach any memory within the 1 megabyte range. Might not be the default data segment, flexibility, specific instructions, which are, yes, while using DS for the source. Okay. Do segments still matter? Segments are largely irrelevant when the processor is in protected mode, as it supports flat memory models and virtual memory management. Okay, we got to deal with them here though. Okay, cool. Yeah, so this though, as a reminder, this is just less efficient because, I mean, probably the speed is basically as fast, but it just takes more bytes to represent. Okay. And this also said before, yeah, this is doing ESDI. Cool. Okay, let's do something a little more fun then. Or let's maybe keep going here. So we'll keep our, well, do we? Yeah, we'll keep our clear interrupts. We think we understand this now. This is cool. This is cool. Again, if we boot, do we need this guy? Just saw there's a floating window. Let's get rid of that. Don't think we're going to need that. Let's run it, right? Our computer works. I think what I really would like to figure out though is put a password on the bootloader. I don't even know what does that even mean here to put a password on the bootloader. We want to encrypt our bootloader or something and then self-decrypt it. I don't know. I want my keyboard to do something, right? This computer right now is pretty lame that there's nothing, like I'm typing on my keyboard and nothing's happening, right? I want to see stuff happen when I type. Okay, how do we deal with that? That's the next question. I would like, so we've got some ability to do output to our monitor. How do we do input? Okay, we got the monitor momentarily figured out enough for now. Let's go ahead and figure out how to make the keyboard work. Okay, let's make the keyboard do something now. I want it to type the letters to the screen. Let's see what ChatGPT has to say about this. Okay, I had a feeling we're going to deal with the interrupt stuff. Is this the same acronym IDT, interrupt descriptor table, as before? No, we had an ISR. What the heck's the difference? Interrupt service routines versus interrupt descriptor table. Okay, I guess we got two things, or they're the same thing. I have no idea. Which is a bit complex for a simple bootloader. Oh. Okay, I see. We can either set up interrupts, or we can just keep pulling the keyboard controller. Let's see what it chose. So we can pull and just keep being like, okay, what's the current pressed key? Okay, what's the current pressed key? Or somehow make it so that on keyboard press, code aggressively diverts and handles that. Steps to handle pulling, read the key code, display the character, right? This makes sense. Okay, video memory offset, start. Okay, we got ourselves a loop. Call get key, call print car, jump main loop. Okay, we got two functions we're doing in a loop. Get the key, print the key. Okay, how do we get a key? XOR AX AX. Okay. So I'm kind of curious, why the heck can we not just move this straight into ES? Is that really not an option? Anyways, XOR AX AX in AL in. Okay, so this is a new instruction. The in instruction. In AL64, I'm guessing this is specifying where we're getting input from and where I want the value to go to. Probably AL, maybe? I don't know. Test AL1, so is this thing equal to 1? If it is equal to 0 instead, loop. So we're just rapidly looping until this thing says that there is a key being pressed. At this point, I guess there's a keyboard buffer. Okay, so 64 tells us keyboard controller status. 60 tells us the most recent thing in the keyboard buffer, I guess. I don't know how many bytes or how many keys the keyboard buffer can hold, but we get to pull maybe the most recent thing from that buffer doing this. This is abnormal assembly to me, but I think we could probably roll with it. Sure, it's very standard. Print character in AL at the current cursor position in ESDI. Print, so print character means, okay, so 0E, which this is white on black. As we learned, the first byte of that AX register is our color scheme. And then, oh, I guess AL, yeah, in AL. AL is holding the key we pressed, which I guess is ASCII. And then we're just changing the upper byte of the 16 bits to that. Do our stow SW thing, ret. Do it all again. Okay, I think this code makes sense. I've got some... I mean, this just looks a little magical, like what the heck's this? But I think the hardware is basically just doing that, or is there firmware doing that? I don't know who makes these in instructions actually work. But let's roll with it. Okay, we booted. Did we boot? We booted. A. Nope, keys are not coming through. Oh, nope, they are. That does not look correct though. Hello world does not type hello world, but we do have something going on. That's pretty cool. Okay, it responds. It does respond, but maybe not as much as we would like. Why is it yellow? Yeah, that's a good question also. I thought we decided that 0E was going to be white on black. Didn't I figure out, though, that F was black? I think it's confused. Well, no. Well, let's see. 0F. Let's see if that changes it. Or at least what that does. Well, now nothing's showing up. Oh, now it is. Oh, I guess I have to click on the screen to make sure that the input goes through. Okay, so now we have white on black. Which is, I guess, nice. But it is definitely not print an ASCII. Why are you not printing ASCII? Is this thing not giving me ASCII? Okay, here's what I want to do. I really regret skipping operating systems course right now. I don't know. When I took an operating systems course, we talked in theory about the bootloader. We never wrote a bootloader though. So this is my operating systems course did not cover anything related to this other than maybe at a textual description. I think the current operating systems course, so you maybe write kernel modules, which is pretty cool. We didn't do that, but I learned a lot about concurrency in my operating systems class. Okay, so I want to debug this thing. My first question is, what the heck is the value of AL? Is it at least ASCII and then this nonsense is messing up? Or is this not even coming in as ASCII? That's what I want to investigate. I could, of course, talk to ChatGPT and be like, yo, you gave me some broken code, give me non-broken code. And maybe it likely would fix things. Yeah, I suspect the keyboard is not mapped to ASCII. I remember having to interact with the keyboard in Java in high school, and there are some weird values there. It's also possible that's the case. I want to try and set up, though, GDB. We'll leave that there. Okay, so let's look at the man page for this. I believe if I do -S or something like that, I am going to make this thing boot with a GDB stub thing attached to where I can like GDB attach to my system, which is like wild, but I think that will literally just work. Help grep -S. Freeze CPU at startup. Maybe it's lowercase s. -S. Shorthand for -GDB TCP 1234. Yeah, so let's add in that. Maybe we also want capital S. I don't know. And then let's do run.sh. I guess we don't need to be paused right at the start. And then we need a new terminal. So this, it thinks, is going to be, what, port 1234? So I think if I do GDB EX attach 1234, it'll connect. Nope, that's not correct. Localhost 1234. I thought it was. I thought this is how you did it. What do you mean illegal? Why are you looking for a process? Do TCP. How do we attach? How do I GDB attach to port 1234? It did say 1234, right? I think it's 1234. 1234. Yeah, so this says this is, oh, it also wants capital S. I guess the question is, do we want to debug the very first instruction, etc.? I don't really care about that. Oh, it's target remote, not attach. Okay, that is why. Target remote 1234. Okay, look at us. We are executing at address 7C12. What are my instructions? Here we go. Look at this. How cool is this? Aren't we happy we have the ability to debug? Oh, someone's saying debugging in real mode can be a pain in GDB, I remember. About to find out. I'm hoping that's not true, but we will find out. Oops. Maybe we also want a debug.sh. We'll deal with that in a second. Okay, so we're going to do a step instruction. Oh, this is constantly pulling. Okay, so we're constantly in a tight loop polling, and there's no keyboard thing, right? So it can continue forever. And it's not blocking or something like that. This is a non-blocking. I don't even know if there's a way to make in block. Probably not. It's like literally what's the current state? What's the current state? What's the current state? So what I want to do is I want to break here. Here. Continue. Okay. And then give me my monitor. Come in here. I type some keys. Okay. Step instruction. Print AX. Isn't that... Oh. Well, I don't know what key I hit. Okay, hold on. We got to restart this. We got to do this a little more principled. Because I may have just hit that key. Wait, what? Oh. Display 8i. RIP. Break. Okay. We are only going to press A. Okay. Print AL. Oops. Yeah, that looks like it's part of our problem. That does not look great. This, in fact, is not ASCII A. I'm pretty sure I did it right. I feel like a whole bunch of stuff in this buffer. What the heck is going on here? Because I held it down for like a while, or how are things coming through still? Okay, now there's nothing in the buffer. But none of these were A either way. I just switch back. Okay, that doesn't... Like, click? Oh, click does do something. So that's good to know. A click is, in fact, interacting and making a bunch of stuff happen. And like, I don't know, we just broke like 3 or 4 times, but a click will do something here. Okay, just an A. Display CAL. Continue. 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 Okay, so that just is nonsense. Here's what we're going to do. We're going to ask GDB to explain what the heck's going on. Or ask GPT to explain what the heck's going on. But there are important notes that I guess we didn't read. Keyboard encoding. The simple example assumes your keyboard directly corresponds to an ASCII character, which is not true for most key codes. Okay, it already did warn us. You'd need a lookup table or handling routine to convert key codes to ASCII characters or handle special keys. Okay. Oops, don't want that. So, okay. Let's remind ourselves one more time. We continue. Why are... Even just like a focus event seems to be doing something. Yeah, literally just switching over is doing something. I don't know if a key is making its way through. Because obviously we have B and C also like doing stuff. A. So we got 30. Negative 98. Negative 32. 29. Negative 32. Negative 99. We always get a lot of negative 32s. 30. Negative 98. Negative 32. Okay. Here's what we're going to do. let's assume I have a normal keyboard. Yes, just to be real clear, American keyboard. How? Show me translation logic. Involves handling both the key press and release events. Keyboards generally send what happens? Keyboards generally send a scan code when a key is pressed and another when it is released. Okay, so it makes sense, right? We press A, we release A. Often the press scan code prefixed by 0xF0 to indicate a release. Okay. Handles some keys. Just creating like a lookup table. Okay, what is it changing the logic to? Read from the buffer. Check if it's a key release code. So if we ever get F0, hold on, let's do D2, R2. How do I delete? Oh, whatever, we'll just do display /XAL as well. Continue. Did I lose my monitor? What the heck happened? A. Okay, I clicked, so that's definitely going to do something. I just pressed A. So I see a 1E came through, a 9E came through, an E0 came through, a 1D came through, an E0 came through. None of those were whatever ChatGPT said. I should have seen a key release code. We're seeing multiple E0s. E0 definitely means something. I'm going to say I don't think I'm seeing F0s, but I am seeing E0s sometimes. Indicates an extended scan code, which is used for many non-standard keys on modern. I'm just pressing A, what the heck? When you see an E0 prefix, it means the following byte should be interpreted as part of an extended scan code. Okay, why are we extended? There's definitely no F0. I'm pressing keys. We definitely aren't getting F0s. I mean, I'm guessing we're going to skip over that E0. Check if it's extended key. Read the next byte. Check for 4D. Example, right arrow key. Definitely aren't getting F0s. Recognize and process E0 scan codes. Read, compare with E0, handle extended, call print hex. Okay, here's what we're going to do. We need a GDB script here for sure. I'm getting bored of hitting C a lot. CD boot. We are going to create debug.gdb. Attach, or what was it? Something remote. Oops. EX. Target remote 1, 2, 3, 4. Target remote 1, 2, 3, 4. We want to break at this address. Let's see what the heck is in AL. We will do break this. And then how am I forgetting the syntax? Is it commands and then done? And we want AL continue. Continue. I think this is the script we want. GDB. We also need to save this thing. ls gdb x debug.gdb. Okay. Fix my GDB script. What did I do wrong? Oh, I need a star. Yeah. Good call. Someone in chat beat Jippity to it. I'm guessing Jippity also probably got it though. Yep. Cool. Okay. I thought we'd said continue. Let's see here. If I type in A. Yep. Okay. 1E, 9E, E0, 1D, E0, 9D. Same thing happened if I switch back over. Nope. Okay, so part of it has to do with how I'm switching between these two virtual monitors. If I hold down control while I swap between like this, it doesn't generate events. If I let go, it does generate events. So let's do a switch over here. It's like I'm about to press Control 3 and it's picking it up here on both like my Mac to switch windows and then also is feeding through. So that generates E0, 1D, E0, 9D. So I think that's like, that probably explains the E0 as the extended is because I'm holding control. Let's do it one more time. So I'm going to switch over and then I'm going to switch over. E0, 1D, E0, 9D. Okay, so this is like possibly Control 3 that just came through. Maybe just Control. I'm going to do it. I'm going to switch over. I'm going to press Control a few times. Control. Okay, we can see things are being written. E0, 1D, E0, 9D, E0, 1D, E0, 9D. Is it only... I'm going to switch over. I'm going to press... Okay, hold on, wait. Before we do that, though, create some space. I'm going to press just 3 and then Control 3. Okay, so just 3... did something like this. Here's what we're going to do. Okay, we don't need to be too fancy here. Let's just bring this over to the other monitor. Okay. Hold on. Seeing we've got something open. We're going to quickly close some things just in case. Don't need things being leaked to the stream. I have no idea what's open. I thought I closed all my other tabs. Probably nothing wrong, but do not need ASU stuff being leaked on the off chance that there is ASU stuff open. Okay. That. Cool. Okay, anyways. We're going to bring this guy over here. We're going to put him over here. That guy over there. That guy over here. Okay, now we can see, and I recognize my camera's up in the top. I think we should be good though. What's going on the screen doesn't really matter. A. Okay, so I just pressed A and we got 1E, 9E. 1E, 9E, 1E, 9E. Let's press B. 30B0. C. 2E, AE. What the heck is this scheme? Okay, hold on. Let's... Okay, A. 1E, 9E. B. 30B0. C. Okay, let's see if Jippy has any idea what the heck this is. This is A, B, C. So 5, 9 equals 9E. Might be the break code for A. 3 might be the break. Why would there be multiple break codes? What is this scheme? 2E corresponds to the scan code for C. Maybe add a silent in the GDB command script so it's not as noisy. That's probably a good idea. Let's do that before we forget. I think this is where silent goes. 1E3, like these are like all over the place. There's some like XOR or something going on here where like it always ends with an E and then always ends with the 0. Like this, is this byte just fully redundant? Like, and then E, and then what, is D gonna also have a 0 at the end or something? Are we alternating odds, evens? Which obviously doesn't really make any sense when I say that, but hold on, yeah, let's go to silent. Oh, he said continue. Continue again. Continue for real. Okay, apparently continue does not continue. So we'll just have to accept that we are manually typing continue. And what else did I want? I also wanted to, how do I, GDB, there's also another thing that's annoying. This guy. GDB, get rid of that. It's like a set something, set space blah, set pagination off. Is that what it is? Yeah. Okay. We're also adding that. Cool. Okay. Run this. Continue here. A, B, C. What if there's a way to not get $sign also? But we're getting real fancy with this. I think printf %x al new line. So fancy of a debugging script here. Look at us go. Nope. Percent, that's not enough. I would do like LLX for a long. Is it CX for a single character? Let's see. D, but I thought D is decimal. Oh, let's just do an L. Continue. A. Okay, well, this is just not right syntax. Fix it again. Fix it. Yep. See, Twitch chat also got set pagination off. See, we're comparing Jippity to chat. Unfortunately, I look at Jippity more frequently than chat, but I am paying attention to chat. Let's see here. Okay. This looks beautiful. This is what we want. What did I have wrong? Oh, we need commas. Okay, whatever. Continue. A. Okay, well, this is definitely not what I want. How to do just one character? C, but I don't want, probably was that comma issue. 0 to CX instead of a long, I think. I don't know how this deals with unsigned stuff. A, nope, didn't like it. What about a single unsigned bytes printed as hex? Yeah, quit being so chatty. Just show me the command. 02x. Isn't that what I had before? I don't want this negative stuff though. I don't want FFFFF. Yeah, but does it not understand what I'm saying? I feel like it should understand what I'm saying. Oh, all right, fine. We can AL and FF. All right, let's see if Twitch chat said that first. That would make sense. I'm sure there's got to be a different way to do that, but that should solve our problem. Let's see here. Did Twitch chat get that one? Oh, look at this. I pull up Twitch chat just and with FF. Not bad. Not bad, Twitch chat. Not bad. Okay. A, B, C, D, E, F, G. Okay, this is a wild pattern. H. Okay. That's pressing lowercase a through H. 2 bytes come out per press. Explain this schema. What the heck is this format? Appears your keyboard or emulator is sending 2 bytes per key press, 1 when the key is pressed down, the make code, and 1 when the key is released, the break code. This is typical behavior for keyboards communicating with the PS2 protocol, where each key event generates 2 distinct scan codes. Make code, break code. Send, which key is pressed, send. It typically equals the make code plus hex 80. Okay, that does in fact line up with what is happening. We are adding hex 80. Okay. But then why is A 1E and then B is 30? Like, why are they not next to each other? Okay, let's break down make code for A, make code for B, make code for C, make code for D. Like, what is this scheme? For example, auto repeat. I mean, I guess we can check. What happens if I hold down A? I'm holding down A. A bunch of 1E's and then a 9E. That's fine. We can roll with that. Make code key press. You might initiate an action, like adding a character to a buffer. Okay, but how do I translate 1E to A and 30 to B and so on? What is the pattern there? Because is this not a mathematical pattern? Am I just gonna have a lookup table here? Like, there's gotta be some sort of something that makes sense. Oh, is this? There's no way it's going off QWERTY. Is it, if I press A and then S, are they gonna be next to each other? A, S, D. What? Why is this QWERTY? G, H, J. Okay, that's absolutely absurd. I'm sure there's a reason for it. I definitely did not think QWERTY was going to be the pattern here. I mean, I guess it's like physical hardware. These are the buttons next to each other. So, okay, so Q is up here. 1, 2, 3, 4. So if I want to handle 1 through 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. A, S, D, F, G. Okay, and then wait, so this is 1, this is Q, this is A. Wait, so A does not, it's not like it's 16 bytes per, okay, 1 0 and then 1 E. Does A follow P, or is this square bracket? So P and then square bracket 1 9 1 A 1 B 1. Okay, so there's like backslash. I don't know how we get all the way here. It's absolutely absurd. Okay, I think we're gonna have a lookup table. I don't know how else you could possibly do this. I think we need a lookup table because we got to get to ASCII to print to our screen. Oh, look at this. Okay, well, I don't want C, but we ain't doing C. Give me my bootloader assembly with the lookup table. Okay. I think we should still be able to fit. Well, this is doing sections. We're going to see what happens here because I think we got like 512 bytes to play with here. DB 02, does that line up? 02 is in fact a ASCII 1. 02 03. Okay, so Q is a 10 according to this guy. I don't think that's true. Oh no, it is true. Okay. Jippity knows this schema. More entries as neat. All right, fine. We'll deal with that. Okay. So we got global start. I'm a little concerned on how this is going to work here. Let's see what happens if we try and assemble with some sections here. What is the assembler going to do? Got to remember, we can only emit this 512 byte thing. I think if we want more stuff, we got to start doing more fancy stuff to get at more sectors or whatever. Okay, this is... I'm worried about getting back to this, but here's what we'll do. We'll copy this, put it in a little nice temp file over here, just in case I want that back. Bootloader code. Okay. Do we have a section? No, but we did have... We gotta specify this, I think. Well, okay, no, this ChatGPT is gonna have to tell us what to do. You're missing... Where the heck does this stuff go? I mean, I know bit 16 can go at the top, but org7c00, we have to somehow say that the text section goes here. Don't think this is gonna... I don't know. How the heck does NASM know where to put this? All that comes out is a 512 byte file. How is NASM going to figure this out? Like, it's fine if we are intermixing our code and data, I think. I don't think that's an issue, but this, I'm pretty sure we would start execution right here. I don't think we can start execution right there. Get key. Okay, so this all looks the same. Print character. Translate. So scan code to ASCII plus BX. Okay, this is going to do our translation. How does NASM figure out how to assemble this thing and fill in my 512 bytes correctly? Yeah. But this, okay, whatever. We'll take its word for it. I am highly skeptical. Here you go. I don't think that this is gonna work. Okay, if this file starts with 00 ASCII 1 ASCII 2, it is making some stuff up. Okay, the thing assembles, but all right, let's just see what happens. Take its word for it. Okay, it's doing something. Now, it's not doing what we want, but it is slowly filling in black text. Just something. Can this thing stop? Don't show me. I mean, it's responding to keyboard. Okay, hold on. What is objdump-d mint, or I just hex dump this thing. Bootloader.bin. Does it actually? Okay, well, sure enough, it puts the data at the end. Wait, but this is... Aren't we outside of our 512 bytes though? This does not sound good. lsalh bootloader.bin. I'm thinking, yeah, this is not good. I'm pretty sure we can only see 512 bytes right now. I'm pretty sure we don't even get to see this right now. So it's probably just addressing, it's probably doing our lookup table, but it's just null bytes. Like, I think we have to figure out how to read from the disk to pull this into memory if we want this in memory. So that's not going to work. I'm going to kind of cheese this a little bit. We're going to get rid of the data section. This is just going to live with the code. Get rid of section.txt. We don't have sections here. Start. Well, maybe we can have a symbol. You can have a symbol, sure. No, we don't need symbols. Start. Okay, before we do this, before we fill in the rest with null bytes, it's going to go right here. Okay, we're just going to live in code. Okay, let's see if this works. Refresh. A, B, C, D. Okay, so that's still not working. We are hopefully now 512 bytes though. We are. And these things are now living right after our code, which is fine. Just don't set the program counter there. Yeah, so someone in Twitch chat said the color might be off, which it definitely could be. So AH is becoming 0E. Isn't that what we had before though? No, it was 0F. Let's try 0F. Oops. A, B, C. Okay, so I think we are going to want to debug. Can we, if I GDB target, how do I get my symbols? Target X8I RIP. Don't think we have our symbols. If I do this on bootloader bin, is there any chance I get my symbols? We don't get our symbols. How do I get my symbols? I guess we need, in the issues, we don't have an elf. I think GDB parses like an elf to find symbols, and we definitely do not have an elf right now. That's so sad. Let's see if Jippity can tell us about that. When I debug, I want symbols. How can I tell GDB about some symbols? to be clear to the person saying kind of sort of close to following what's going on, need more study. I mean, I don't really know. I've got, I mean, some ideas of what's going on, but I am pretty lost here as well. I just know that I'd like to debug this thing. And basically what I want to do right now is I want to be able to say like break get car or something. I don't want to say this because every time I change my program, this address moves. I want to not deal with that. Okay, so we can generate an ELF64, I guess. That we can do that, sure. Is that just gonna work? Okay, so you'll spit out a bin. You'll also spit out an ELF. Wait, where? For example, if your has a label starting, assuming or okay, I could create my own .sim file. I mean, we can write logic that'll parse our assembly to create a bootloader.sim. We're not going to do that. Let's do this. I think that can work. Okay, we'll say this is for symbols for GDB. Here's our 512 bytes blob of data for the hardware. Bootloader. Let's boot with GDB and a drive and default VGA monitor. I don't know how many cores we have right now. I think we got one core. I don't know how much memory we have. We can specify cores in memory here, but we're not dealing with cores in memory until we got a reason to do that. Okay, so that add, no, we don't want that. Use. Okay, I think now what we can do here is let's, well, we can just do this and then do bootloader.elf, which does not exist yet, but is about to exist. And we'll just throw that as a comment right here. This is how we debug. Oh no, we want -x debug.gdb. Okay, let's do this then. We run it. Error parser instruction expected. Okay, so someone's not thrilled about us. We want to build an elf. This ain't how you build an elf. Doesn't know how to parse this to create an elf. Use a stub for symbolic debugging. Well, we're definitely not doing that. Can I make NASM spit out a .sim file? Here's the issue. We need to be able to debug stuff. This is like crucial to understanding what the heck's going on. If we have any chance of making stuff work, we need to be able to debug it. And right now we're working on our debugging infrastructure. Can I make NASM spit out a .sim file? So the .sim file looks really simple. Like I could almost just like not spend too much time and generate this thing myself. It's literally just address space symbol name. Like that's pretty good. Like that's not bad at all. But yeah, manually create, but I don't want to manually create. Add symbol file, generate a map file. What the heck is this thing? Yeah, now it's going to tell us, here's how you can convert a .map to a .sim. Okay, well, does this thing work? What comes out? Bootloader.asm map bootloader. What? NASM help grep -L. Write listing to a list file. What was the other argument? -map. Is it not map? Is it -M? Probably -M. Now, whatever the heck app is. Generate makefile dependencies on standard out. Okay, I don't want that. Okay, what if we just do this -L thing? Screw the map. What is the list? Cat bootloader.lst. Oh. Okay, so if I want to generate these symbols myself, that looks so annoying though. It's kind of cool that it can generate this, but I don't. Okay, we're gonna take a pause on this. We're just gonna specify addresses. We're gonna be sad. Actually, yeah, we're gonna take a pause on this. We're instead going to just use the address. Okay, so run.sh, let's get rid of this thing. Just kidding, this don't work. Okay, let's gdb -x. Okay, here's what we want to see. Disassess. X8I RIP. We want to look at our. Why the heck is there? This does not look right. If I say IP, EIP, I don't think that this is correct. So registers. Print PC. X8I PC. See, this is looking at these instructions as this. I don't think. I told you GDB in real mode is a pain. Is this the part where it's a pain, where it's not parsing my instructions correctly? Because I don't think we have RDI. Okay. Entire state is off. Is there a solution to this problem? How do I see my instructions? How can I x/8i RIP, but instead for 16-bit real mode? Twitch chat thinks they know how to print this stuff. Using CS and IP in GDB. x/8i $CS times 16 plus $IP. That was a nice idea. x8i $IP. This does not look correct. Why can't I paste anymore? GBay may automatically. How do I tell GDB 16-bit? We're gonna make this keyboard do something. You need to set the architecture to I-8086. Doesn't sound so bad. Set architecture I-8086. Let's see if that works. I wonder if we have to do that after we attach. Ooh, that does not look good. Let's pretend that doing that after we attach is going to make it work. There's a whole GDB script for that. How do I copy this? Copy. I copied the whole message. Paste. Oh, nice. Okay, let's see what the heck this is. Oh boy. That looks pretty cool. Don't know if I want to use something this crazy though. Step over calls. Define step until code. Step until ret. Step until iret. Step O. How does this thing have the context? Prints the stack. Prints all of this stuff. x/i RIP, but it's also doing x/i RIP. Set real mode. I'm thinking that it's this part. I should probably zoom in a little bit. I think it's this part that like does it, but I'm thinking that QEMU doesn't know how to handle that with QEMU. Let's see if Jippity can work on this in the background. With QEMU system, how to make work. GDB thinks your code is in 32-bit, and the disassembly is obviously incorrect, even with correct using, because it assembled the wrong code. Linear memory instead of segmented memory. We got to patch QEMU? Oh my. Don't know if we're going to be doing that. I mean, we can if we have to, but this seems like not what we're trying to do. It's going to miss the change. Probably QEMU devs don't care much about 16-bit real mode. QEMU doesn't want to deceive GDB. QEMU starts lying about the true values of these things. Okay, here's what we're going to do for now. I think what we're going to do is try and avoid this. See if we can debug in another way. I guess one of the goals is going to be to get out of real mode. Yeah, I think out of real mode and into protected mode as quickly as possible. This is like something you do something to the CPU and suddenly it's in a whole new world. The CPU is like running two architectures. I don't know the correct terminology here, but we need to get the heck out of real mode as quickly as possible. This is a nightmare. Something that we now know, as was warned to us early on, that you're not wrong. Looks like GDB is a disaster with this. Okay, how do we debug though? I think we can We can make it work. Let's generate that -l file, because that's going to tell us where we want to break. -l, what was the -l thing called? -l bootloader.lst. bootloader.lst. Okay, so we're going to do run.sh. We got our lst file. I think that gives me at bootloader lst, or maybe even let's just open this file so we're ready to go. Okay. Where do we want to be pausing? This translation is happening incorrectly. Print character. So we call get key does XOR this, wait for key. Eventually, then we pull it out, put it into AL. Sitting in AL now, we make this 0F. Put AX into BX. Why are we saving it? I mean, I guess just in case we want it back later. BX plus this thing goes into AL. Wait, this order of operations does not look correct. Okay, I think I see the issue. Jippity gave us some bad code. Anyone else see this issue? I think we have an issue here. We're using the 0F thing as part of our index into this, but I don't think we want to do that. I think we discovered that 02 is a 1, 03 is a 2. Okay, so what that means is plus 0 should end up here, plus 1 should go here, plus 2 is here. But we're adding 0F here into this high byte. But why would we do that? Don't do that. We need to get rid of that. We don't care about this. Get rid of that. We need to style it after we look it up. Look it up and then style it. So we're going to take AL plus this thing, right? So this gives us our number. For example, 02 will come out, and that should give us ASCII 1, assuming this lookup table is correct. Then we style it after we look it up. Then we do it. See, ChatGPT, it can write some code. It's not bad, but it's not, certainly not perfect. Okay, I've got a good feeling about this. Let's see. Some of our lookup table is missing. What happened? Invalid effective address on line 127 or on line 27. Can you not do this? Let's hope that that's the high byte is 0. Let's just move AH0 in AL. No, we XOR'd it. I got a good feeling. It's already 0. What? Can you not do plus AX? Move BX AX plus BX? Do I actually have to do that? You can't address with AX? What is this mode that we're in? Real mode is... So I think we've seen like on pwn.college, right? When we're like writing assembly, it's like certain instructions don't just, there's no encoding for it. So you like assume you're like typing plus AX. Like, of course, there's going to be an instruction that decodes for that. Wrong. There's not. We kind of put it in BX and then whatever. Okay. Let's see here now. Okay. 1, 1, 1, 1. Look at this. A. Oh, look at, okay, B doesn't exist. Did we map B? Why does B not do anything? We probably didn't map it. We didn't map it yet. 1, 1, 1, 1, 1, 1, 1, 2, 2. Also, how big is this monitor? Oh. 3. We're also getting like a white space, but if we hold it, there's no white space. That's a feature, not a bug. It allows us to see how long we held it. Look at this. We can type to the screen. Are we getting major PogChamps in Twitch chat? We're getting wow cools. That's good enough. Never trust GPT. Sometimes, you know, people say that programming is dead. ChatGPT is going to do it all. Maybe one day. And ChatGPT, you'd notice ChatGPT was still extremely useful. It did things that I have no idea how to do. But I do know how to read some assembly and, you know, use my brain a little bit here and say that we should not be styling our character before we go into the input table. That does not make sense. So you know what? Use GPT, do a little bit of debugging. In this case, we did some static analysis instead of dynamic analysis. Fix the bug. All right. Why does this... I guess I'm just not showing the entire monitor. That's fine. I guess we could zoom out probably a little bit. There we go. Yeah, there we go. Look at that. Well, that's awesome. Okay. So if we wanted the rest of the table, right? So for example, if I press C, if I press 1 and then C and then 1, right? See, like I press C, that's why there's all that emptiness. We don't have C mapped in here. Okay, we're missing part of our table. But that's okay. We don't need to be complete here. We got QWERTY. What more do you need, right? I can QWERTY. So we got that mapped in. And I think we still got space in our bootloader. If we wanted to do more stuff, we'd look at xxd bootloader.bin, right? This 512 byte blob. Look at all these zeros. So much room for activity. We don't get these 2 bytes right here say it's a bootloader. Look at all these zeros. We could do so much stuff still. Plenty of room to do more logic. So I guess the question is, how do I get out of real mode now? And do I want to get out of real mode? Can I still write to video memory if I leave real mode? Or can I only do this in real mode? Let's see. If I leave real mode, can I still write? Okay. First of all, let's make sure it understands. This is corrected code. You messed up. Make it feel bad, but in reality, we're just making sure this is in context. So that if I say something in the future, it knows. Now it's just sad. It's upset with me. Yeah, okay. Oh, look, it even knows what we did. Especially with the proper initialization and handling a register BX before accessing. See, it knows what it did. It's not going to lie to us. It knows it messed up. Let's review for clarity. Yeah, okay. We don't need to talk too much. I just want you in context. Okay. Now let's leave real mode and go to protected mode or whatever the heck the next step is of normal bootloader stuff, right? So right now we're in like 16-bit real mode. I think the next step is to go to 32-bit mode. Maybe you can go straight to 64-bit. I don't know if you can go 16 to 64, if you have a pit stop in 32-bit mode. I have no idea. Let's ask, can I go straight to 64-bit? Do I still get to write to video memory directly, etc.? Let's see what it has to say about that. Because I would prefer to write assembly that I know about. How can you then load the code you enter in input? Wait, what's that question? How can you then load the code you enter in input? I mean, so for example, in theory, I don't know if I fully understand your question. I think in theory, when we're running, it's up to us to do whatever we want, right? We're drawing to the screen. If you're saying like, how could I like write new instructions to memory and start executing that? I mean, I think we could, right? Like we could imagine parsing this as hex, right? If I like parsed hex and then on whatever way we want the system to work, it suddenly writes to memory, and then like I press another key and suddenly it sets the program counter to where we just started updating instructions, and suddenly I have like this region of code where I can write instructions to memory with my monitor and then suddenly go execute it. Probably we could write that program. Be a little advanced. I don't know we're too interested in that. Maybe that's not even what your question was, but we could do whatever we want, right? We just got some hardware, some code, we're doing it. Okay, transitioning to 64-bit long mode. 16-bit real mode to 64-bit long mode in a bootloader involves several steps, and it's more complex than just switching from real mode to protected mode. Don't know what that means, but okay. Let's break down the process. Transitioning to 64-bit long mode. Enter protected mode. Before you can switch to 64-bit long mode, you must first enter 32-bit protected mode. Okay, I guess that answers that question. This is because switching directly from 16 to 64 is not supported. Just the architecture says no. Like, it is what it is. Setup GDT. You need a proper GDT setup in protected mode. This includes defining at least a null descriptor, a code segment descriptor, and a data segment descriptor, whatever that means. If you're at home reading this with me and you don't know what that means, I don't know what that means either. Enable PAE, physical address extension. Enable PAE by setting the appropriate bit in the CR4 control register. So I have heard about these control registers. They're just like fancy magical registers that make the CPU operate in yet another way. This is necessary to enable 4-level paging, which is required for long mode. I think this is getting at like starting to enter the world of virtual memory or something. Like we're getting paging set up. I think paging is part of virtual memory. And like we got, I think 4-level means we got like 4 layers of indirection. It's like this points to this, points to this, points to this. And here's the actual physical address. And if you have this thing, you walk this thing until you get to the physical address. And that's how you translate virtual to physical addresses, I think. Setup paging. You must set up and enable paging with a 64-bit page directory and page tables. This step is crucial because long mode requires a specific paging configuration. I think these are our 4 layers that we were talking about before. Where did it say? 4-level paging. I think these are the names of the different levels of those 4. Set FRLEME long mode enabled. Modify the MSR model specific register to set the LME bits, which signals the processor that you intend to enter long mode once paging is enabled. Again, I don't know why we don't set with stuff default setup. There's probably a reason. I'm sure there's a good reason. Enable long, what is this button on Jupyter? Reply? Can I reply to a single word? You can't. Weird. Enable long mode. Finally, enable paging via the CR0 register. So we got CR0 register, CR4 register, the MSR model specific register. We got all these fancy registers. These things are like RAX and RBX, but they're got way more meaning to them. They're not just like a place to hold data. They tell the CPU you are now operating like this. Jump to long mode code. Okay. In 16, so that answers the rough outline of getting to 64-bit mode. What that actually looks like, we don't know yet. But we got the high-level overview. Handling video memory in long mode. In 16-bit real mode, you can write directly to video memory starting at this for text mode. In protected and long modes, things become more complex. Okay, this is why we like 16-bit. It's like simple land. Protected mode and long mode. Once you enter these modes, especially long mode, direct hardware access, including direct video memory writes, become non-trivial due to the use of virtual memory. Direct access to this address, like in real mode, is no longer straightforward because all addresses are virtual and must be correctly mapped to physical addresses in your page tables. So that means we might be writing to some virtual address, I think, that then corresponds through 4 layers of indirection to this physical address. I think as long as you write to this physical address, you're chilling. But along the way, you're really writing to a different virtual address. Maybe you can make the virtual address also be this, and then that corresponds to this physical address. I don't know. That's something we can really do or not? Probably we could. I don't see why not, but we'll find out. VGA text mode. You can still use VGA text mode in protected and long modes, but you need to set up your paging correctly to map the physical address blah to a virtual address that your program can use. Okay. Because I think then once we're in like this long mode and we like specify an address, the CPU is going to like automatically walk this page table thing to like resolve it. Like the hardware does that, I think. Frame buffers for graphics. For graphical modes, modern bootloaders and operating systems use a frame buffer provided by BIOS or UEFI interfaces, which might involve setting video modes via FBE, VESA, BIOS extension, or UEFI GOP, Graphics Output Protocol. Can you go straight to 64? It's technically feasible to set up a bootloader from real mode to long mode as long as quickly as possible, bypassing much of the functionality traditionally used in protected mode. It requires careful setup of the paging structures, the GDT, the IDT, and paging structures. Basically, we got to become compliant with what the hardware wants before we can switch modes, because then the hardware is suddenly going to use these structures that we've set up in our 64-bit mode. So we got to set them up before we switch, because otherwise the hardware is going to try and use our setup things, and if they're not set up correctly, I don't know, maybe the CPU faults or like fails, or I don't know, something probably bad happens. Most practical implementations briefly enter protected mode to set up the necessary structures for long mode. Okay, so this roughly describes to us our task at hand. Now the question is that something that I'm going to do right now? Or are we going to pause, as in stream another day? That is what I must now decide. Have we made enough progress for today? I mean, I could even stream tomorrow, right? It doesn't have to be once a week. We'll figure out on what basis I want to do this, but I think that might be cool. I think probably 2 hours is a good window of time. We got to work on some real stuff. So yeah, let's do that. Let's see here. What did we create? So we got our bootloader. What have we accomplished today? What do we understand now? Got our bootloader. It's in 16-bit mode, which is just basically the CPU architecture supports this, like, in some ways it's like just a fundamentally different mode of instructions. It's like very similar to our normal x86 64-bit stuff we're used to. It's in like a different mode and things kind of operate a little bit differently. We got to set up these segment register things. For example, we can access video memory, which is at like this physical address B800. Is basically just like magic land, where if you write to it, you're suddenly appearing on the screen, right? It just does that. This other stuff is IPXE and booting from hard disk. That showed up from someone else. I don't know who did that. I think probably the BIOS or whatever. But at this point, our bootloader, we write to this address and like through, I don't really know, maybe BFFF or something, like this region of memory, if I had to guess, something like that. It just draws ASCII on the screen, right? Put ASCII in and it shows up. If you just write to memory here, it's just magical, right? The hardware does this, right? That's what we mean when we say it's magical. The hardware is just looking at this region of memory or something. And then the hardware takes care of it. Of course, we've got a virtual display. The virtual display is our hardware, okay? It just knows to read from here, and the hardware just does something probably not dissimilar than this, and it just like is rapidly reading memory as fast as it can and then drawing pixels, as in like lighting up things in the physical hardware. Okay. So we write to magic this address. We wrote this program. We know how to interact with the keyboard a little bit now. The way we interact with the keyboard is we do this in instruction. I think in just stands for give me input. I don't really know what this thing is, but input from the 64 thing. I don't know, like, for example, 60 is the keyboard buffer, 64 is the keyboard controller status. Somehow these things are just magic value mapped. We want to read here, we get the keyboard controller status. That ends up now in AL. If it's a 1, then that means there's stuff in the buffer. If it's a 0, that means there's nothing in the buffer. So we just keep looping forever. If it's 0, loop forever until it becomes there's something, there's a status, and then we get to pull from the keyboard buffer. And I don't know how big the keyboard buffer is. We could ask Jippity. The keyboard buffer might be like 1,000 bytes or something. I don't know. But this is how we read from the keyboard buffer. That gives us this weird QWERTY thing where like 0, 2, like if 2 pops out of AL, that really corresponds to ASCII 1. And then 3, and then you'll notice here, right, QWERTY, like literally QWERTY. So at, I don't know, offset 16, right, hex 10, if we get a 16, that's really a Q. If we get a 17, that's really a W. If we get an 18, that's an E. So we just build this table as a lookup table. And all that means is that we take the value that came out, which makes its way here, blah, 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 blah. And we take the base of this, we add something. So for example, we might add hex 16. If BX is 16, which came from this in thing, if this is 16, we add 16 to scan code to ASCII, add 16 to wherever this is located in memory. This is just has some base address, add 16, out pops a Q, an ASCII Q. We put that in AL. We do a little styling. This means white text on a black background. If we put that in the higher byte of AX, this is in the lower, we do stow SW, and this just writes to memory right here, and then adds 1. This is basically doing ES and DI. This is a segment. This is our index kind of, it's just a register. This is a general purpose register. It's RDI. It's a 16-bit version of RDI. It does this segment plus here, and adds 1, I think, to DI. So stow S1 just increments DI, writes to memory ultimately, makes sure that we're going to write to the next place in memory. And by writing to this magic location in memory, we have written to this VGA, I think it's VGA, screen, and the hardware takes care of the rest. And we do this all in a loop. We fill the rest of the space with null bytes because this thing is 512 bytes. Somehow the hardware magically knows to look for a 512 sector thing. Really, it's just blob of bytes, xxd bootloader.bin, blob of bytes. It knows to look right here. It sees that. And QEMU, our virtual machine, boots this thing up, starts execution right here. CPU starts decoding instructions, doing its thing. All the hardware does its thing, blah, 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 blah. And ultimately, we have this sweet program where I can type to the screen. And if I hold A, it keeps doing that. Let go. I'm pressing B. B doesn't exist because we didn't map it in our table. We could map it in our table, but we only have through L. I don't know, something like L. Maybe even semicolon. Quotes. Enter, maybe, I don't know. A. We don't have Z, X, C, V, B, N, M. We just don't have that in our table. We could add it to our table though. And this is this. I don't know what happens when we get to the bottom of the screen. We might crash things. Who knows? This is like, so if you think about it, right? We have this thing that just keeps incrementing by 1. At some point, I'm going to just hold this down as I talk. At some point, we're just writing byte to memory, next spot in memory, next spot in memory. At some point, we're going to leave this video thing of memory. We'll just keep adding 1 to it. And suddenly we're going to be pointing at an address that's outside of the bounds of this, which is like probably not good. Let's see here. We're like halfway there. This is feasible. We could have probably manually added 200 to the start to deal with this. Let's do that. Let's get our buffer overflow. This is taking too long. We will bootstrap this by doing add di, I don't know, 500. That will make it start over there. So now we're here. Okay, 500 is not much. Let's do 5,000. Well, now we're not typing at all. We went too far. 2,000. All right, each one of these addresses just corresponds to like a single text piece of memory. Okay, we're almost there. Probably do the math on how wide this is, how tall it is. $4,000 too far? What was it before? 3,000. 2,000 it is. Every time I do this, I'm rebooting. Okay, we're gonna rapidly press. I don't know if I saved myself time by doing this. But at some point, we are no longer writing to the right piece of memory. And we're writing over something else in memory. And who knows what that memory corresponds to, if that's a magic address that also does something or not. But if you've seen things where like the Tetris thing where like starts becoming weird colors and shapes, I think it has to do with a similar thing to this. Like the code just doesn't account for this overflow. Obviously we could account for the overflow, but you could imagine, yeah, see, it doesn't like wrap around or something. Like we're just writing further and further into memory. And at some point, I don't know, maybe it's like 4096 is the total. I don't really know. But I think we're writing somewhere else and that's doing something, and maybe it's not an important piece of memory and it really is just memory. I don't know. But that is what we have created today. That's what we've done. Thank you all for those of you who decided to attend and to watch. Let's see here what's going on here. We'll see some questions. What is the goal going to be by the end? That's a good question. I don't have a goal necessarily specifically clarified yet. I do want to develop a pwn.college module on this. So somehow I'm going to create challenges that require people to do, like, pass some sort of test cases. So that's going to be one goal. Now, what's the end goal? So I have an idea in my head of what I want to figure out. One direction I want to make sure I go. One is going to be, I'm vaguely familiar with the fact that, you know, we've got 512 bytes here. I want to figure out how we load other stuff into memory. Like, I think similar to like this stuff, there's a way to like start reading from the hard drive basically. And then we can read from the hard drive and like pull it into memory, or maybe we can literally map it into memory. I don't really know what that looks like. I want to clarify that. How do we get more than 512 bytes? I want to figure out how we get to 32-bit mode. Like, I want to actually go through the process of going to 32-bit mode. I want to go to 64-bit mode. That would be really cool. And another thing that I vaguely want to do is I want to, so one of the things that QEMU supports, if we look at QEMU system, x86 64, man, this thing, oops. This thing supports like, where is it? This. You can like plug in hardware that is like a network device, okay? I want to use this flag with QEMU and do whatever the simple basic network device is. Like, I want it to be the equivalent of our virtual machine, virtual hardware. Like, we plug in an Ethernet cable and suddenly TCP packets are flowing in. I want to do, maybe we don't handle TCP. We don't need to build that way up, that high up. But I want to at least do some level of networking. I don't know. Maybe we start with Ethernet, like like a MAC address and that sort of thing. Maybe we start with that. Maybe we build all the way to IP. Maybe we build all the way to TCP. Maybe we have our code, like a packet comes in, we automatically check if it's an ARP packet and we do an ARP reply. I want to basically figure out networking. And maybe like one kind of crazy idea, we'll see if we go this far, would be, so in 365 and Intro to Cybersecurity, we have this module that's called Building a Web Server. I might build a web server either as a bootloader, so it'll just respond to an HTTP request and return 200 OK as a bootloader, or maybe we need to get into real mode or like protected mode, I mean, or 64-bit. I don't know. Maybe we need to go up. Maybe we stay in 16-bit. I don't know. We'll see what makes sense there. I would like maybe to build, maybe, I don't know. We'll see where we go for sure. But I think maybe building a web server would be cool. Maybe building a shell would be cool. I don't think like, we'll see. We'll see what parts of like an operating system or like standard technology stack there is. And I think we're going to implement some of that. Like, I'm not going to like try and be POSIX compliant or Unix compliant or something. I'll probably borrow a lot of ideas. Like maybe at some point I'll create like a concept of a process and figure out like, you know, you type the syscall instruction and somehow a normal kernel handles that syscall. Well, maybe I'll figure out how to handle a syscall and I'll create a couple of syscalls and we'll have a concept of a process. Maybe we won't. I don't know. We'll see what we want to see where we go with this. But I think it'd be cool to also have a concept of a process somewhere baked in here. Kind of figure some of that stuff out. So there's a question. Mostly though, I'm just gonna like start doing stuff and then asking ChatGPT and see if there's terms I don't understand, follow that. So I see a question that says, are bootloaders usually written in assembly? Aren't they written in C? So I think writing it in C is pretty common, and maybe we'll see. We'll see if I get kind of annoyed with writing lots of assembly. I might just stick to assembly. Kind of like makes it feel a little more real. Obviously, we could probably switch to C and figure out, you know, how to make C emit an ELF, and then whether our bootloader or whatever sort of thing knows how to parse this ELF and map stuff into memory. That might also be cool to like figure out how to, you know, get C connected into all of this. I know, for example, like we would avoid dynamic linking, at least in the short term. I know that you can get GCC to emit this like static ELF thing that doesn't have the C runtime being used, right? So it doesn't have a main function because main implies the C runtime is calling into main. We can get rid of all that stuff and still write C. I don't know, maybe that'll be nice. Maybe I'll figure out how to statically compile Python and put that somewhere in our hard drive and figure out how to launch that thing, and we'll be writing everything in Python. I don't know. Probably not. We might stick to assembly. I don't know. We'll see where it goes. Anyways, thank you all for those that decided to attend. I haven't decided yet on what basis I'm going to do this, but I would like to do this again. This was fun. And at some point we'll start generating levels, and I don't know, we'll just go. I'll also make sure everything ends up on YouTube. And I don't know, maybe I'll pre-announce before a stream or something, or maybe I'll just do it. I don't know. But anyways, thank you all for attending. Good luck with whatever you guys are doing. And I will see you next time, whenever that is. Goodbye.